Alright, in this video, in this homework, I'm going to ask you to draw the pi molecular orbital system for the allyl cation. So an allyl group is simply a double bond and then one carbon. So for instance, as a common name, this would be called allyl bromide. You don't really have to know that. That's for nomenclature. Allyl is not a proper name for it's a propenyl group. But that's a common name. You'll see it if you wind up in any job that requires use of chemicals. You'll probably see the word allyl from time to time. Anyway, draw the pi MOs for allyl cation. Go ahead and hit pause. So here I'm only looking for the pi orbitals. The sigma orbitals are going to be made up of the overlap of sp2, sp2, or sp3, or sp3, or sp, or whatever hybrid orbitals. The pi orbitals are just going to be made up of the p orbitals. That's what I want you to draw. Alright, hit pause, work on that, come back. Okay, if you're back, again, identify hybridization. Carbon-carbon double bond, 3 things bonded to it, right? 2 hydrogens not shown in this carbon. So that's sp2. Same goes for that carbon. What's the hybridization of a carbocation? I haven't explicitly talked about this. It's in the book, so hopefully you've seen it. How many things are bonded to the carbocation? 1, 2, 3. 3 things are bonded to the carbocation. There's no lone pair. There's no fourth object of any kind. So the hybridization of a carbocation is actually also sp2. Okay, did you draw a resonance structure of this molecule? If you haven't, so if in doing the MOs you didn't draw a resonance structure, hit pause, draw an important resonance structure of the allyl cation. Alright, go away and come back when you're done. Okay, so you can just simply move these electrons over to there. The resonance structure then looks like this. Looks like you've just flipped it over, but you've actually moved. If we number these, if we number the atoms, 1, 2, 3, 1, 2, 3. So the overall structure, what's the relative stability of the 2 resonance structures? They're exactly the same, right? They're completely symmetric. You can overlap the structures. Again, if you can overlap the structure, I can take this structure, I can take the resonance structure I drew, and I can exactly overlay it with the original structure. They have to be equally stable. Okay, so the overall structure then looks like that. Sorry, there's a charge. So that positive charge is sort of delocalized over the 3 atoms. It's actually a fairly stable carbocation. I'm going to erase some of this, so if you want to write it down, go ahead and hit pause. Or you could just wait for me to do my thing. Okay, I asked you for the p molecular orbitals, or the pi molecular orbitals. So go ahead and give those a shot. So we've got carbon bonded to carbon. That's the sigma bond network, right? So carbon sigma bonded to the middle carbon, which is sigma bonded to the end carbon. In organic chemistry, all the carbons will always have 1 sigma bond. They may have no more bonds than that. If they're single bonded to one another, they have 1 sigma bond. If they're pi bonded, they have a sigma and a pi. If they're triple bonded, they have a sigma and 2 pi's. But you'll never have a double bond where they're both pi bonds, for instance. Okay, sp2 hybrid orbital, so there's 1 p orbital there. sp2 hybrid orbital, there's 1 p orbital there, and in fact that's our pi bond, right? There's the pi bond. Once again, we get to that carbocation, carbon 3. That carbon has an sp2 hybridization, so it's going to have 1 p orbital, like so. And now look, a pi bond is simply 2 p orbitals separated by a single sigma bond. That's exactly what you have here. In fact, you can't tell looking at this. If I hadn't drawn this here, like let's go back. I'll draw it down below. I'll draw it over here. Right? That's the hybridization. Those are the molecular orbitals. Those are the p orbitals on each atom. Where's the double bond? You can't tell from this because it could be here, it could be there. So really, you also have a pi bond here. And what you really have is 1 pi molecular orbital. that's delocalized over all 3 atoms. And that is, in fact, the whole point of the resonance. Sorry, I don't think you can see that. Right? Remember this structure I drew, where we have delocalization over the whole thing. When you can draw a resonance structure, you actually have delocalization, such as is shown here in the pi molecular orbital system. Okay, so I hope you got that. I hope you understand it. If you have any questions, rewind it. Maybe come and talk to me.